This webinar is entitled Modeling a Ring Resonator with Multiple Round Trips Using a Fox-Lee Algorithm. This webinar is the second webinar in a series integrating SimphoSOFT Active Modeling into VirtualLab. Why do we want to use SimphoSOFT with VirtualLab? Today I'm going to show you an example of a ring resonator, which is shown here on the left and on the right. If we use VirtualLab only to model a ring resonator, we're only allowed to use one laser beam, in this case the seed beam, which goes around the cavity. If you want to model a gain material, you'll have to use an analytical approximation using fixed photokinetics. The fixed energy level diagram is shown here on the left with 4 energy levels. And the analytical approximation is given by the gain G up here in the left-hand corner. However, if you model a ring resonator using VirtualLab and SimphoSOFT, you gain several advantages. One, you can use multiple beams in your model. For example, 2 or more beams. In the example today, we're going to have 2 beams, a seed beam, which goes around the cavity, and a pump beam, which goes through the cavity. Second, using SimphoSOFT with VirtualLab, we are using a full numerical solution with no analytical approximations. The energy level diagram can be much more complicated than the 4-level model. For example, up here in the corner, I show a neodymium energy level diagram with the standard 4 energy levels plus 2 additional levels. This situation can easily happen with neodymium because neodymium has an extra energy level up here such that the gap between this level and this normal level is about equal to the gap between this level and the lower level. That means the process of upconversion can occur. Upconversion occurs if you have 2 ions close to each other with electrons in this state. If upconversion occurs, then one of the electrons loses energy and goes to the lower level without emitting any light. And that energy is used to transfer the second electron up into the higher energy level state. A second reason that you can use the more complicated SimphoSOFT energy level diagram is that in real life, many of these energy levels can undergo splitting by the field inside the gain material. For example, this level may split into 5 levels, this level may split into 5 levels. If your pump spectrum is not wide enough to encompass all those levels, you'll get a different answer than would be the case if these were single levels. So these are 2 reasons why you would want to use SimphoSOFT with VirtualLab to model gain materials. The outline of the webinar is as follows. First, I'm going to talk about SimphoSOFT features and benefits, then talk about some of the VirtualLab features and benefits. VirtualLab is a program that's sold by LightTrends. The example I'm going to show today is a ring resonator amplifier with multiple round trips. After the demo, I'm going to summarize the results. Note that we're looking for your feedback. After the webinar, it would be helpful if you could send us your requirements for your simulation needs that may need the use of both SimphoSOFT and LightTrends. You can send your requirements to support@symphotech.com or to service@lighttrends.com. Also note that on the SimphoTech website, you can chat with us and submit written questions if the live chat button is on. What are some of the SimphoSOFT features and benefits? There is a new feature in version 3.2 called the Material Excitation Map, which is a 3D map of the populations of all the energy levels. This excitation map stores the final material energy level populations at the end of one simulation run and uses those values as initial conditions for a second subsequent run. This type of situation is needed if you're doing multiple passes through a material, such as an amplifier or a laser. Over on the right are 2D plots of what these excitation maps would look like in 2 dimensions. You'll see plots of populations. For example, here is the ground state. Populations in red are high populations, blue are low populations. You'll see the populations as a function of radius out from the center of the beam and as a function of distance traveling through the sample. So this is a 2D plot of what an excitation map would look like. In the program, we're actually using 3D plots as a function of radius and distance to the sample. Another feature in SimphoSOFT 3.2, it's a new feature, is a SimphoSOFT Link to VirtualLab. You have access to the SimphoSOFT numerical engine from VirtualLab. That's illustrated schematically down here. You can set up a sample with energy levels in SimphoSOFT, and you can run SimphoSOFT from VirtualLab, so you can run both programs together. SimphoSOFT also has all the previous features and benefits, some of which are listed here. You have both linear and nonlinear actions of light with photoactivated materials of any type. You can do photokinetics modeling, where you have an unlimited number of material energy levels, an unlimited number of optical transitions, and you can use the program to calculate what the energy level populations are using rate equations. Simultaneously with the solution of rate equations, SimphoSOFT also does beam propagation of the light going through the sample, either for pulsed or CW beams. SimphoSOFT can handle multiple beams, 2 or more beams of light, and you can optimize material properties in SimphoSOFT. Here are some examples of material energy level diagrams and transitions that you can set up in SimphoSOFT. The one on the left is AF455, an organic molecule, which has 3 singlet states, 2 triplet states, and you see different transitions, including a 2-photon absorption here. In the center is an example, a simple example of neodymium YAG showing only 4 energy levels. This simple model is what we're going to use in the webinar today. On the right shows an example of much more complicated energy level diagram that you can set up in SimphoSOFT. Instead of just having 1 ion in a material, you could have multiple ions. The example here has 2 ions, ytterbium with 2 energy levels and erbium with 8 energy levels. Also shown are approximately 30 optical transitions, including absorption, energy transfer, upconversion, and relaxation. So these are the types of complicated situations that you can set up in SimphoSOFT that's not available in VirtualLab. Now for VirtualLab features and benefits, here are a few listed here. VirtualLab has great flexibility in source propagation and detector modeling. For example, you can set up just about any kind of source model, any type of detector model, and you can set up any type of optical components, such as lenses, gratings, and so on, in your optical system. And so you can do modeling of components and modeling of devices, such as lasers, amplifiers, and microscopes. VirtualLab enables optimization and analysis. You can do things such as laser systems, gratings, computer-generated holograms, femtosecond pulse setups, resonators of lasers and amplifiers, and illumination systems for LED light shaping. These are just some examples. Another useful feature is VirtualLab is customization. For example, you can integrate another program with VirtualLab. Today I'm going to show you how to integrate SimphoSOFT with VirtualLab so that you can run SimphoSOFT from VirtualLab. The example we're going to show is a ring resonator with multiple round trips. A 3D view of the resonator is shown on the left with 3 mirrors, a gain material, and a starting and stopping plane. This is shown here as the VirtualLab light path setup, where you see the seed, the 3 mirrors, virtual screen, and the amplifier. The amplifier is where we're going to include SimphoSOFT and run SimphoSOFT from VirtualLab. To use the programs together, you set up a supporting SimphoSOFT project with the beams, in this case a pump beam and a seed beam, and an energy level diagram. In this case, we're going to use the 4-level model for neodymium. And you get an output in VirtualLab. The steps in this demo are as follows. The first step is we're going to do a material pumping, where we have a gain material inside the ring, and we're going to set up a single pass of a 500 watt pump through the gain material for 250 microseconds. We're going to set this up in SimphoSOFT, create a link file to use the SimphoSOFT file in VirtualLab. We're going to run the single pass of 500 watts for 250 microseconds from VirtualLab by accessing SimphoSOFT. And then we're going to store the material excitation map. We're going to store the final energy level populations after the pump beam is going through, and use those as a starting point for the amplification part. Note that we need to have this pumping step in order to excite electrons in neodymium to excited states so that stimulated emission and amplification can occur in part 2 of this demo. The 250 microsecond pumping time is longer than any of the relaxation transitions in neodymium and will result in the excited states of neodymium being significantly populated to approximately steady-state conditions. The second part of the procedure is the seed amplification. In this case, we set up two beams, a pump beam and a seed beam. They're each going to be 100 picoseconds or a tenth of a nanosecond long, and they're going to be propagating simultaneously through the gain material. We're going to set this up in SimphoSOFT, and again create a link file for running SimphoSOFT from VirtualLab. We're going to use a Foxley algorithm and run 6 round trips of the seed and 6 passes of the pump through the gain material. After each iteration, we're going to store the excitation map of the populations, electron populations of all the energy levels, and we're going to use the excitation map stored during the previous excitation and use that as the starting point for the following excitation. So what is the Foxley algorithm that we're going to use? The Foxley algorithm is going to be supplied by LightTrans in VirtualLab. It's going to be used to determine the most stable transverse eigenmode by simulating multiple passes through the amplifier, and it's going to be used to look at the amplification. Using the Foxley algorithm, you start with a seed beam. In the most general case, you can start with a random phase beam and run that through the system, but that's a slow process. It's going to take many passes through the system to converge to a solution. However, if you think you know the approximate final eigenmode, you can use that as a starting point. For example, we're going to use a Gaussian single mode field as a starting point, and that's much faster because you're closer to the final solution. With Foxley, you do multiple passes through the ring resonator. This may take tens or hundreds of passes in some cases. For example, if you're starting with a random phase until the solution stabilizes. We're going to calculate the dominant transverse mode, and we're going to calculate the gain. And we're going to do the demo with 6 passes of light through the gain material. Now we're going to go to the demo. Before we go to SimphoSOFT, I want to show you what the project directories will look like stored on your hard drive. Normally in the SimphoSOFT directory, there will be a project directory where you have all your different projects. We recommend for integrating SimphoSOFT with VirtualLab that you set up a second directory. You can call it VL integration if you want. And inside that second directory, you'll have a projects directory for the SimphoSOFT projects. That is currently empty, and we'll start filling it up during this webinar. The other was a VirtualLab scripts, which we will supply to you. And we're going to use scripts for a multiple pass ring resonator today. So now I go to SimphoSOFT. The program is open here. On the left, normally you'll see a project list here of all your different projects. We want to go to that new directory that I just showed you. You can do that File, Project Folders, and you pick the new directory that I just showed you that has VL integration and a subdirectory of SimphoSOFT projects. So that's going to be your project directory for these new projects. SimphoSOFT comes with the many template projects. These projects include projects that will utilize VirtualLab. To get to those projects, you go to File, New, and there's a list of all the template projects that are supplied by SimphoSOFT. To use the ones that are related to VirtualLab, you go to Import Export, click on VirtualLab, and this lists the template projects that involve VirtualLab. The ones we're going to use today are these two here, the final two. We're going to click on this one, which says neodymium YAG pumping. We're going to give it a project name, neodymium YAG pump microsecond BL. And you hit create. And this project will be imported as a new project in SimphoSOFT. And you'll see two screens here, one showing here is the energy level diagram. It's called MCAD. The second is called ECAD. Let me make it smaller. And in ECAD, you have the laser beam and the sample. The laser beam, if I right-click it and look at properties, first the beam power. Let me change microwatts to watts. It's going to be a 500 watt beam. Beam radius is 1.5 millimeters. The length of the pulse is 250 microseconds, and it's going to be a box-shaped pulse in time. Wavelength is 808 nanometers. The radial profile of the pulse is Gaussian. There are many possibilities to choose from. We're choosing Gaussian. The temporal shape is this flat top box, which we use to simulate the CW applications. Again, there are other possibilities, but we want the flat top box. Okay, so that's the laser beam, and that's going to go through the sample. Now let's go back to the MCAD here, which is our standard 4-level model that we're going to use today with the simulations. But if you want to do something more complicated, let me show you how to do that. You can add energy levels. For example, to add an energy level, I click on the energy level icon. Let's choose default parameters. Let me put the energy level here. Let's go in and look at its properties. I'm going to give it the E symbol like the others, and I need to give it an energy. For the other energy levels, I've been using inverse centimeters. For this one then, I'm going to put in 20,000 for inverse centimeters. And you'll see here that the gap between this level and this level is essentially the same as the gap between these two levels. So we have the possibility for the F conversion. And I can put that in by clicking F conversion. Let's choose default. Here's the symbol. I'm going to put the down arrow here and the up arrow here. So this is my F conversion transition. Again, when you have F conversion, an electron in this state goes to the ground state without emitting light, and the second electron gets that energy and goes up to this state. Neodymium can have several energy levels between here and here. I'm going to ignore that for now and just put in one relaxation transition. Let me put it in here. So that shows relaxation transition, up conversion, and a new energy level. So this is a type of ease with which you can change the energy level diagram. I'm not going to use this more complicated diagram today, so I'm going to remove these. Just delete them. So now then, I've basically kept the original energy level diagram. So now I want to generate a supporting project that will link SimphoSOFT to VirtualLab so that later I can run SimphoSOFT from VirtualLab. To do that, I go to File, Customize Export. It's going to give me a XML file up here automatically. I'm going to change the run name. This is a run name where we're running SimphoSOFT from VirtualLab. I'm going to call it RunVL. I want to generate an excitation map. And I want to generate an excitation map in some directory. Okay, I'm in the project directory now for this new project. I want to generate a new directory, subdirectory, called runtime VL. Okay. And then runtime VL. Go to runtime VL. And in runtime VL, I want to set up a new file name. It's going to be an XML file. And this is a file where the location of the excitation map is going to be stored. Hit OK. And I'm just going to click on this, include session ID, and hit OK. And now the linking file has been generated. To see that, I go to my directory. Here's my directory under SimphoSOFT projects. my neodymium YAG pump microsecond VL, click on that, and you'll see this new file, neodymium pump microsecond VL, with a VL INI label. And this is a file that's going to be used by VirtualLab to run SimphoSOFT from VirtualLab. And here's a new directory. I'm going to store the location. Right now that directory is empty. Okay, I'm finished with SimphoSOFT for now. I'm going to close SimphoSOFT. So now I want to go to VirtualLab. I open VirtualLab. And I want to open the file pump simple. So here's the light path. It has a pump, the gain material, and a screen. The gain material is where we're going to run SimphoSOFT from VirtualLab. This is done through a script file. I double click on the gain material. And I want to go to field tracing. And here's a script file. I want to go to source code editor. So this script file is what is used to run SimphoSOFT from VirtualLab. You do not need to worry about the contents of the script file except for the path here. The other parts we give to you. The path, when you first open it from your computer, will not have the correct path. To insert the correct path, you go back to your directory. Here's the path of the directory that contains this INI file. You can copy that path, go back to VirtualLab, and insert that path here. And make sure there is a 1 backslash at the end. So this didn't change because I already had the correct path, but you will need to do this on your file to put the correct path for your computer. That's all you need to do for this script file. Click OK, and OK again. Now all we need to do is run the file. I'm on this light path. I click Go. Okay, you see the pump beam here, and the program is running. It'll take a few seconds to run. It's almost done. Okay, let's look at the output, so ignore this one. Let's look at the reduce field, and reduce field at the halfway point. The initial here, the incident, is the starting field. If we go to data view and view over here, you'll see this is the 500 watt starting field. At halfway through the sample, if I click here and data view, the power of the pump has dropped to 284 watts. And at the end of the sample, at the output of the sample, look at data view, the power of the pump has dropped to about 156 watts. So the pump was pumping electrons into the higher levels of neodymium YAG, and the pump power, as it went through the sample, dropped from about 500 watts to about 156 watts. I'll close VirtualLab. And if you go back to the SimphoSOFT directory for neodymium YAG pump microseconds, you'll see now there is a run VL, which has all the files that SimphoSOFT generated when it was running from VirtualLab. In the runtime VL directory, there is now an XML file which contains the location of the excitation map. So now we go back to SimphoSOFT. I've opened SimphoSOFT. Now I want to generate the project for the amplification. I go to File, New, and in these VirtualLab files, I want to look at the last one here. I'm going to click on it. I'm going to give it a name, neodymium YAG -nanosecond -VL, and hit Create. Here is my project. It has the 4-level energy level diagram for neodymium YAG, which I'm going to keep. If I go to ECAD and look at the experimental CAD, you'll now see there are 2 laser beams. This is a pump. I change this back to watts. You see it's still the 500 watt pump. Same beam radius as before, but now I'm going to have a box-shaped pulse that's 0.1 nanoseconds or 100 picoseconds long. That's for the pump. If I look at the seed beam, it's going to be a much smaller beam. It's going to be 2 microwatts. But again, it's going to be 0.1 nanosecond long and box-shaped. So now I have the 2 beams. I have the possibility of a delay in between the beams, but I'm not going to use the delay. I'm going to keep the delay 0 so that the 0.1 nanosecond pump and 0.1 nanosecond seed beams go through the sample simultaneously. So I've not changed this project. This is the original project that I uploaded from the SimphoSOFT templates. Now I want to export this to VirtualLab, but first I need to do one thing. Let's go back to my directory. You'll see that in my original file, my pump microsecond file, there's a runtime VL directory with this XML file. This is a file that contains the excitation map for the pump after the pump is going through the sample. I need that same information as a starting point for my amplification run. So I want to take this directory and file, copy it, go over to the SimphoSOFT project. You'll see there's now this other new project, the nanosecond project, and I want to paste this runtime VL into that directory so I can use that from this directory. Okay, so now I'm ready for exporting to VirtualLab. I go to File, Customize, Export to VirtualLab. There's going to be this new file generated with a nanosecond VLINI label. Again, I want to change the run name when I'm running to have a VL label. I want to generate an excitation map, and I want to generate the excitation map starting from this run VL location. And I want to use this run VL XML file and generate other excitation maps for each round trip. To do that, I click on Use Excitation Map. The re-enter time, we're going to have a time of 100 picoseconds between each round trip. Beam index, I'm going to set that to 0. And I'm going to include session IDs here. If I click OK, it's going to generate the file that's going to be used by VirtualLab. To see that, I go back into my directory, and you'll see in my neodymium YAG nanosecond directory, there's now a new file, neodymium YAG nanosecond VL.VLINI. This is a file that's going to be used by VirtualLab. Okay, so now I close SimphoSOFT. And I want to open VirtualLab again. Okay, this time I want to go to File, Open. Now I want to do the amplifier gain round trip. Open it. This is again a file that's supplied by us that will be used to run SimphoSOFT from VirtualLab. Here is the light path, which has a seed beam, 3 mirrors, and the amplifier. If I click on the amplifier, we're going to go to the text file, the supporting text file. Again, I want to go to source code editor and make sure the path to this neodymium YAG nanosecond VL.VLINI file is correct for my computer. I've already changed it. It's correct. I don't have to do anything. Click OK twice. If you want to look at the 3D image, I can look at the 3D image of this path. You can see it here. It has the 3 mirrors, it has the sample, has the starting and ending planes. Now to run this file, you'll notice that the light path only contains a seed beam. I have to supply the pump beam. So I'm going to open the pump beam. This is this 500 watt Gaussian pump beam. So that's shown here. Instead of running the program from this light path, we're going to run from Fox-Lee. So I click on Fox-Lee, open. Here's the Fox-Lee script, which again we supply for you. There's not much to worry about here. The only thing you can check is the simulation maximum iterations. It's set to 5. The program will actually run 6 iterations when it's set to 5. The other thing to check is this simulation normalization field power set to false. If this were set to true, the program would renormalize the field after every round trip. This would cancel out any amplification. By keeping this normalized field power on false, the Fox-Lee algorithm will do both looking at the best eigenmode and looking at the amplification. To run the program, I make sure I'm clicked on Fox-Lee and press go. And at first it'll ask me for the light path. The light path is the one I just showed you. It's this light path. Also asks me for the field each time I do a round trip. So that's listed here. I'll click OK. It's going to do the first round trip. The way the program is set up now, I need to manually choose the pump field each round trip. So choose it again. And so forth for each round trip. This will take a few more seconds to finish up. Okay, Fox-Lee has finished its run. And I'll show you 3 plots here. One is the dominant eigenmode. You'll see that the dominant eigenmode is a Gaussian single mode. And 2 other plots here. One is the phase, one is the amplitude of the eigenmode. And in phase, you'll see the phase stabilizes after just 1 iteration. And you can see an amplitude. Amplitude changes but then stabilizes after a few iterations. So that's calculating the eigenmode. Now let's look at what happens in the amplified field. This is the final field here. I go to Data View and view it. You'll see the final field is about 81 microwatts. Now I started out with the seed at 2 microwatts. The gain is a little over a factor of 40. I can also look at all the fields after each round trip. I'm going to erase the seeds. I'm going to erase this and look at the amplified fields at each round trip. Again, I'm just erasing the seeds. Just about done here. Okay, so I'm done. I've started out with this seed field. Again, it's about 2 microwatts. After the first round trip, the power is about 3.4 microwatts. After the next round trip, it's almost 6 microwatts. The next round trip, 11 microwatts. The next one, 21 microwatts. This one is 41 microwatts, and then the final one, which I showed you before, of 81 microwatts. So this shows you running SimphoSOFT from VirtualLab and running the Fox-Lee algorithm. So we got 2 results. We got the dominant eigenmode. We can see the total gain of the 6 round trips and the individual gains at each round trip. So now I'm going to close VirtualLab. If you go back to my directory for neodymium-YAG nanosecond, you'll now see the run files for all these runs. And in runtime VL, this XML file will contain the location of the excitation maps for each round trip. So I finished with my demo showing you how to run SimphoSOFT from VirtualLab or an amplifier project. So now I want to finish up. First, to summarize the advantages of using SimphoSOFT and VirtualLab together. SimphoSOFT, you can set up excitation maps for multiple material excitations. So you can use an excitation map from one pass of light through the sample and use it as a starting point for the next pass and so forth. SimphoSOFT has the ability to use multiple beams. We use 2 beams today. And SimphoSOFT has the ability to set up an unlimited number of energy levels and transitions, such as shown over here on the right. These can be set up with an easy-to-use SimphoSOFT graphical user interface. SimphoSOFT can model both linear and non-linear actions of light with materials. In terms of VirtualLab, VirtualLab has the great flexibility in source, propagation, and detector modeling, being able to use just about any kind of source model, any kind of detector model. You can model optical components and devices, and you can link VirtualLab to other programs. Today we showed you how to run SimphoSOFT from VirtualLab. Example applications where you might want to use both SimphoSOFT and VirtualLab together include lasers, amplifiers, which I showed today, rare earth applications, optical limiters. In the life sciences, you can model multiphoton microscopy, super resolution microscopy, flow cytometry, fluorescence imaging systems, and so forth. If you want a 30-day evaluation of SimphoSOFT, go to our website and click on Free Trial button, and we will send you a 30-day evaluation, which is a full version of the software. Mind you also that on the SimphoSOFT website, you can do a video chat when it's open, where you can submit questions to Symphotech. Additional information, you can go to the Symphotech website at symphotech.com or the Lighttrans website at lighttrans.com. You can email me questions at bsandk@symphotech.com, or you can send questions to support@symphotech.com or to service@lighttrans.com. Symphotech runs webinars from time to time, and you can go to our website and click on webinars to see the schedule for any upcoming webinars. Again, we are looking for your feedback to design better software products. If you have applications that can use both SimphoSOFT and Lighttrans together, send your applications to us. I'd like to thank you for attending today's webinar. Have a good day.